Okay, welcome. This is our new recitation 8. Actually, in this recitation, we will basically focus on actually in some sense again the inline integrals of vector fields, and also, our main item is Green's theorem. Okay, in this lecture, we will essentially focus on Green's theorem and its applications. And of course, we will, if you remember, last time we have discussed conservative fields and again line integrals of vector field. And today we will briefly keep discussing those topics, and then we move to the concepts of Green theorems and its applications. Okay, first problem. So let's see. So we have a curve, and actually, this is so C is a kind of a curve, the curve of intersection. Actually, we don't care the shape of C. Remember, if you remember last time, we actually used the idea of path independence. But to do this, we need we need a kind of a conservative vector field, if you remember. So let's check. First, we just first check if the given vector field, the vector field. So remember, so this is just a line integral of a vector field, but which vector field, which is, let me call it f. So f here, so the first component is this. Okay, y, okay, pi minus e to the z, and the second component is, okay, pi x squared cosine pi y minus 3 e to the z. This is the second component, and the final and the third component is this. Okay, and we have to check whether this vector field is conservative or not. Okay, fine. So let's try to check, and just a small, just a quick observation. Just notice that. So if you should check the necessary conditions, right? So just notice that. So we have those conditions. So the first condition is, remember, f1. Let me call it, this part is f1 and this part is f2, the second component, and this part is f3. And if you compute this partial derivative, you will immediately, easily see that we have this. Okay, so it is fine. But at the same time, if you compute the partial derivative of f2 with respect to x, you have exactly the same result, right? For all xy in the domain, right? Domain of f, and domain is actually everywhere, right? And this is the first observation, and the second observation, right? So we are trying to check the necessary conditions. Remember, we did this last time, right? We had so many examples. And the other condition is, so we have to check this, and if you compute, this is just minus e to the z. And on the other hand, if you compute partial derivative of f3 with respect to the first variable, right, you have exactly the same expression. So everything looks great so far, but now we have a problem. So if you check this thing, so partial derivative of the third one with respect to second variable, right, this is 0. But if you differentiate f2 with respect to the third variable, right, so what is it? So this is just minus 3 e to the z, and which is never 0 actually. So we have a problem, right? So over here the condition fails. The condition fails. What does it mean? The meaning is, actually, game is over. So f cannot be a conservative vector field. So that means that, so f is not a conservative vector field. So f is not conservative. Okay. So fine. Remember, if we, remember the last time. So if we end up with a kind of a case, then what we actually what are we supposed to do is just use direct computations. But here, using direct computations by using this parameterization of C is still hard. Still, but the problem is it is still hard to use direct computations. So again we have a problem. So what should we do? Actually, we need a new approach. So here a new trick, if you like, or the new, okay, let me say new trick. So here is the trick, or the new approach. Try to modify f so that f turns out to be actually a conservative vector field. So modify f, actually just make f conservative somehow. So modify f so that it becomes conservative. Okay, so this will be our new strategy actually. So how to do this? The possible approach is just need an extra term. Actually, the missing term, if you like, in, for instance, f3. Remember, so f3, when we differentiate with respect to y, it was 0, right? Remember. And so that del f3, to satisfy the condition, what we expect, so this should be exactly minus 3e to the z. So how to obtain such an expression? Just, for instance, just to have some idea, just integrate with respect to y, right? Integrate with respect to y gives the following observation actually. So f3, okay, it depends on x, y, z. So if you integrate this expression, okay, this one with respect to y, actually we have something like this, right? Plus h, some function depending on x and z. Fine. Now we have a hint. Here is the hint. Hint is this term. Okay? So we need a kind of a term like this. Okay? So this is the hint. So let's try to use this hint. Okay, fine. So we have a nice hint. So let's try to use this hint in the following way. So just rewrite everything. So rewrite the given line integral f dot dr as follows. Just rewrite everything. So this is our original f dr and the original. So just a small modification will do what we need actually. So this is, so let me write it down, everything. Okay, pi y minus e to the z. This was, remember, the first component. Plus, so nothing changed. So these are the same. Cosine pi y, right? Minus 3e to the z, and this is dy. And finally, the final component. So this is the trick. Now we just add this extra term, or subtract, like this. Okay? So can you follow? So this part is dz, and plus another line integral, exactly the same line integral, and with the same extra term. Therefore, nothing changed actually, right? So can you follow? So we actually add and subtract exactly a kind of a similar line integrals. But now what we have is the following. So let me just consider this part. This is the first integral 1, and the second one here, this is the second integral. But now, because of this trick, so let's see what we have. So now we need to compute actually these two integrations. So we want to evaluate integral 1 and integral 2, the green one and the blue one. So let's try to compute the blue one. Let's evaluate this blue integral. So let's see what we have. Actually, we have a kind of a vector field here. We just let us define a new vector field, which is G. It has exactly the same component as F, but with some modification, with some extra term. Right? So these are all the same. Remember, this is almost the original vector field F, but here we have this extra term. But now, thanks to this extra term here, the red one, actually G, actually then just observe that by definition of G, actually this is how we choose G. Actually, G satisfies all necessary conditions. Okay, therefore now G satisfies basically all necessary conditions for being a conservative vector field. So G maybe, there is a possibility, maybe conservative. Actually, remember, our domain is simply connected, therefore actually G turns out to be conservative at the end of the day anyway. So we just let G to be, okay, let's use phi. Phi is our potential. Then remember how to deal with those things. Then we have the following bunch of equations, right? So we have, okay, del phi del x. Remember, this should be G1, its first component, which is just, okay, 2x sine pi y minus e to the z. And what else? Okay, the phi partial derivative with respect to y. This should be the second component of g, which is pi x squared cosine pi y minus 3e to the z. And finally, this partial derivative, which is this. Okay, which is just, okay, let me write it down. This is just g3, which is minus x e to the z minus this extra term. Okay, so this is equation 1, equation 2, equation 3. So remember how to deal with those things. We just start with any equation you like. So let me start with the equation 1. So integrate equation 1, right, with respect to what? With respect to x, of course, right? Then we get, let's see what we get. Actually, you can easily get the general form of this function or possible candidate, which is this. Just integrate with respect to x. Okay, let's see what we have. Minus x e to the z, right? Plus some extra function depends on y and z. Okay, so this is our actually general, our potential candidate, if you like, in a general form, in a very general form. Then, of course, we should determine, this auxiliary function h in more detail, right? Okay, so let's see what we have. Then we have two equations, actually. We haven't used them yet. Then by equation 2, for instance. By equation 2. Let's see what we have. So equation 2 tells us what? So equation 2 tells us, so this thing, right, cosine, okay, pi y minus 3e to the z. So this is exactly what equation 2 tells us. This should be del phi del y. But actually we can compute now del phi del y, because we know a kind of a standard form or very general form of this function phi. And if you take the partial derivative, you can easily see that with respect to y, of course, okay, pi y and plus del h del y. Okay, so what does it tell us? Actually, okay, this is for all xy, remember, for all points. So these are actually cancel out each other, so which gives that. So let me directly write. So actually you can integrate. Okay, so let me write it down. Which gives something like this, and hence integrating both sides with respect to y gives you a possible form of h. So h should be something like this, e to the z, right, plus some function depends on z only. Okay, now this is actually our more precise form of our function h. So that means that, so it means our phi x y z turns out to be, okay, this term. Now we have more precise picture actually, and minus 3y e to the z plus f of z. Okay, so we have this. But now to find, to determine fz, just now using the last equation, equation 3, remember? So let's see what we get. So we get the following observation. So equation 3 tells us, so this part is exactly equation 3, remember? E to the z, so this is equation 3. This should be del phi, del z, but we have the form of phi. Just apply over here, differentiate with respect to z, so we have, okay, something like this, I guess, right, plus, okay, df dz. Okay, so these are all cancel out each other. So what does it tell us? And so what does it tell us? F df dz should be 0, and so what does it tell us? So it means that f of z is just some constant k for some constant k. And remember, actually we can take this constant to be 0, just k to be 0, then actually we have a potential. We obtain a potential phi for the vector field G, right? So which is just, so the phi turns out to be, okay, x squared, okay, sine pi y minus x e to the z minus 3y e to the z, and f of z is 0. And that's all. This is phi. We have a potential, remember? So this is not unique. Actually, we have a nice potential function such that if you compute its gradient, this turns out to be our vector field G itself. Therefore, we can use now path integrals, right? So therefore, by independence of path, remember the theory, by independence of path, let's see what we have. So we have the following observation. So we don't care what his C is. C may be a kind of a curve like this, so we don't care really. So this is exactly where C becomes, so 0, 0, 0. So this is where it ends. This is only 2 points we need actually, and there is, let me say, some parametrization here at some point rt, for instance. So this is given like this, okay, t and ln 1 plus t, right? Parameterization is given and t runs from 0 to 1, of course. So we have such a curve, but now thanks to this path independence observation, our blue integral, remember the blue one, the blue one, just the integral of this vector field G along the curve C. Now by using this independence of path business, this is just phi the endpoint 1 1 ln 2 minus phi the initial point, right? Just like the fundamental theorem of calculus. Then you just compute and this turns out to be minus 8. Fine, but this is just one part of the story. Remember, just go back. Okay, remember, now we compute that part. What about the green part? I mean this green integral. So let's see, let's compute this part, but this part is rather easy. Why? Compute the second part, compute the integral 2. So let's see what we have. But now this part is not that much hard actually. You will see. Actually, we just use the parametrization over here. So we just using the parametrization. So let me write it down. Using the parametrization. Which one? I mean, just x will be t, y will be t, and z will be, ln 1 plus t, right? And then let's see what we have. So our integral, I mean the second integral, the green one, is just the integral of this term, right? This is just a function. This is just a simple line integral, right? Not a line integral of a vector field, if you like. Very simple form. But now using this parametrization, actually, t runs from 0 to 1. So we have 3t here. And instead of e to the z, we have 1 plus t. Instead of dz, dz will be 1 over 1 plus t dt. Okay, fine. So these are cancel out each other. So the result will be 3/2. So in total, as you should say, kind of a long computation, I'm sorry, but in total, we obtain the following. So we obtain our original integral from, our original integral, the line integral of a vector field f. Remember, f was non-conservative in the first place, but we modify this one, right? And we actually decompose f, if you like, into two pieces, which one of them is this, and the second one is a very simple one. Remember? And actually the first part, this part is now this G component is just conservative, if you like, and then we just compute it, and the result will be, I don't know. So what was it? Minus 8 plus something like this. This is the result. This is conservative part of f, and this one, if you like, you can really consider this thing as a vector field in this form, if you like. That's the simple part. This is the other part of f. This is the conservative part of f. This is some other component of f. So we actually decompose f in some sense, or we modify f, so that even if it's a kind of a complicated integral, actually one part can be dealt with using independence of path theory, and the other part can be computed by using Dirac approach. So this part using Dirac approaches, this part, and this part uses independence of path approach. Fine. That's it. So this is actually a hard problem, right? It's a little bit long, but now actually, I mean, this is how we use conservative vector fields basically. You see, because the other part it's really hard to use direct computation, but we simplify it, we decompose it. One part can be easily computed by using direct computations, the green part, and the other part, the blue part if you like, can be dealt with by using this independence of path theory. Okay, fine. So the next one is this. So now let's try to solve the next problem. Now we have actually a kind of a line integral around a closed curve. This actually rings a bell. Somehow we can use a green theorem. So remember, so green theorem tells us about a connection between the line integral around the curve, of course, around the closed curve, and the double integral on a region enclosed by that curve. Okay, so actually, so we have a kind of a picture, if you like. So we have a kind of a picture like this. So this is our boundary curve C, which is just, okay, y square, okay, 4. This is just a circle, but at the same time we have a region. So region D. D is a region enclosed by, or bounded by, enclosed by the curve C. Okay, if we have a kind of a scenario, actually we can use green theorem. Okay, first note that here D is what's called a regular region. Okay, with a boundary curve, in this case a circle, curve C, which is, okay, x square y square equals 4. Actually this is, which is a simple curve, which means that there is no self-intersection, which is smooth, clearly, right? This is a smooth just a smooth simple, and what else, and closed curve, right? C has those properties with respect to positive orientation or counterclockwise orientation, okay, or positive if you like. Okay, if you have a kind of curve and the corresponding region, then actually we can use green theorem. And actually so green theorem is a kind of a passage from line integrals on a suitable curves, suitable closed curves, and there is a passage between double integrals on some region enclosed by those curves. Okay, so this is actually what green theorem tells us. Okay, this is very briefly. For details, actually you can check the lectures if you like, but this is what briefly green theorem tells us. Then by Green's theorem, let's see what we have. We have the following observation. Instead of computing this thing, okay, this one, okay, dx, okay, a convention in general, a convention is, let me denote this part by P, denote this part by Q, okay, two component if you like, and the green theorem so applies here. So green theorem, so you pass to corresponding double integral, and double integral of this integral del Q del X minus del P del Y, and dA, the area element. Okay, so instead of computing this line integral here, line integral on this red curve, actually it turns out to be the same thing that we can compute the double integral on a region, the blue part, enclosed by this red curve. Okay, but now we go back in some sense the double integrals, right? So but now this is easy because this is d, because del q del x is just 2 minus 4 dA. Therefore we have actually minus 2 times this double integral. But we know that before, I mean, we don't need any extra computation. We know that the meaning of this double integral is exactly the area of the base region, right? This is exactly the area of base region, and actually if you compute, this is just a disk with radius 2, therefore area is 4 pi, therefore the total result is 8 pi. Okay, remember, okay, this is the relation between the area of the base region and the double integral. If you have an integrand 1 right here, so this double integral gives you the area of the underlying base region on which you integrate. Fine, so that's all. This is just a simple application of the Green theorem, and actually in the next problem we will see more complicated usage of Green theorem. But before this, I guess it is a good point to stop. Let's take a short break. Okay, thanks.